Hello, everyone, and welcome to this LIGO over COCAGRA webinar, where we'll be talking about the population properties of merging compact objects using the fifth gravitational wave transient catalog. On this title slide, you'll find a link to the paper on arXiv and on the public DCC, and also a link to the Zenodo repository where the data release for this paper is contained. My name is Sharan Banagiri. I'm a postdoc at Monash University, and I'll be leading this webinar and going through the first couple of sections. Joining me are my colleagues Max Icy from Columbia and Wei Tong also from Monash University. For the last 20 minutes of this webinar, we'll be doing a question answer session, and joining for this question answer section will be joining the rest of the team for the question answer session will be Soumendra Roy from CITA and Mario Spera from INFN and SISSA in Italy. So please, if you have any questions, please leave your questions in the question answer box, or you can also raise your hands at the end of the webinar. Okay, so let's get started. This infographic, it shows all of the gravitational wave detections since the first observing run of LIGO, Virgo, and COCAGRA. We had webinars over the last 2 weeks, which went in more detail on the catalog itself. In this infographic, each of these smaller circles represents a detection. The distance from the center of the circle, the center of the big circle, represents the distance of the gravitational wave candidate itself. The mass of the gravitational wave candidate is represented by the size of the circle, and the opacity represents the signal to noise ratio, or how loud the detection was. So we see here detections from 01, the first observing run, all the way up until 04, which was the latest observing run. The fifth gravitational wave transient catalog, GWTC 5, contains new results from the second part of the 04 run. So this is called 04B, and all of these detections are shown in purple here. So we have 161 new compact binary candidates in 04B, and this brings the total number of detected candidates to 390. If we use a more stringent false alarm cut of 1 per year, this gives us 104 new candidates in 04B, and the total number of candidates from 01, which passed this more stringent false alarm cut, is 267. All of the new candidates in 04B, so all of these purple candidates, are binary black hole mergers, and we do not have any new neutron star containing mergers. And as I said, previous webinars over the week and the week before have gone into more detail on the nature of the catalog itself and on particular events that have very interesting properties. For the paper that this webinar talks about, we are interested in understanding the astrophysical implications of this gravitational wave catalog. So we want to ask questions like, what is the underlying distribution of masses, spins, and redshifts of the population of merging binaries? What sort of formation environments are these binaries forming in? What sort of formation environments are black holes and neutron stars forming? And what is the astrophysics and maybe the stellar physics of their progenitors that dictates their properties? Let's talk about methodology. Gravitational wave catalogs are probabilistic data sets. What this means is that any single event will have a substantial amount of uncertainty in it, generally, often at the levels of 10% or maybe few tenths of percent. So for example, this plot here shows each of these curves in this plot here shows our inference of the primary mass and the secondary mass. So these are the two masses of the binary, and we see that these credible regions are quite broad. These are 90% credible levels. Gravitational wave transient catalogs are also filtered through the instrumental selection effects of the detectors. What this means is that the observed data sets are not fair draws of the underlying distribution of compact mergers in the universe. So we are seeing that our data sets are filtered through the instrumental selection effects. The plot on the left captures this, for example. So this shows the sensitive hypervolume that the detectors can see as a function of the mass of the binary. So, for example, the sensitive hypervolume that we can see for chirp mass of 4 solar masses is several orders of magnitude smaller than the corresponding sensitive hypervolume for, say, 35 solar mass chirp mass. So what this means is that to actually understand the true population level distribution of merging binaries, we have to perform hierarchical Bayesian inference on the population. And this remains the standard way to do these sorts of analyses with gravitational wave data. So in this paper, we perform two different kinds of analyses. The first are called full spectrum analyses, where we look at all CBCs. So all CBC is compact object mergers, so all binary neutron stars, binary black holes, neutron star black holes, we throw all of them in the same bucket and self-consistently try to understand the distribution of all of these merging objects put together. The second set of analyses look only at binary black hole mergers, that's BBH. And this is motivated by the fact that we have more binary black hole mergers than all of the other candidates. So we have significantly more binary black hole mergers. And in the binary black hole merger only analyses, we impose an additional selection effect of requiring that the masses of our component binaries are greater than 3 solar masses. Let's start with the full spectrum analyses, where we look at all of the binary black hole, where we look at all merging binaries. So this includes binary neutron star mergers, neutron star black hole mergers, and binary black hole mergers. These two plots here show the joint mass distribution of all of these merging binaries. So the primary mass, I want you to look at the lower triangles here. The primary mass is shown on the x-axis, and the secondary mass is shown on the y-axis. And these are two different population models. The one on the left is what is called a strongly parameterized model, which makes strong assumptions about what the distribution of binaries can look like. And the model on the right is PixelPop is a weak model, which is more flexible, and it makes fewer assumptions about what the shape of the distribution can look like. And we recover some common features. So for example, we recover a global peak in the mass distribution at 10 solar masses. There is some overdensity at small masses. This corresponds to binary neutron star mergers, and some other features that we will go into in later slides. One nice thing about these full spectrum analyses, where, as I said, we are looking at all binaries in one go, is that we can then convert these sorts of distributions into constraints on the rates of individual classes of binaries. So for example, the binary neutron star merger rate has a joint interval of around 5 to 155 inverse gigaparsec cube per year. So this is the rate putting together or combining both the constraints from both of the two models that we have, which are PixelPop and FullPop. The corresponding merger rates per merger rate densities for neutron star black holes is between 6.7 to 32.8, and for binary black hole mergers, it's between 27.5 to 49.5, roughly speaking. Okay, so that's full spectrum models, but since we did not have any new neutron star containing events in O4b, the rest of the paper and the rest of these slides will look at binary black hole mergers only in detail. Oh, oops. I should say before we get there, sorry. One other thing that we can take away from this full spectrum analysis is that there is we can almost completely rule out an empty mass gap between 3 to 5 solar masses. So in other words, while there does seem to be evidence for a dip in between 3 to 5 solar masses, a completely empty mass gap between the heaviest neutron stars and the lightest black holes is ruled out. Okay, now we'll switch gears and talk about binary black hole mass distribution. And this plot shows the mass of the primary and the mass ratio distribution on the right. Remember that the mass ratio is defined as m2 over m1. So this is the lighter object, the mass of the lighter object over the mass of the more massive object. So Q is always less than 1 by definition. We also have these hatches here on these plots. If you've looked at our population analyses before, you might you will see that this is the first time that we have hatches like this, and these indicate regions where we have less than 1% of binary black hole PE samples. So these are heuristics designed to represent regions of the parameter space where we have fewer detections and less data. So where model systematics and priors can dominate. So if you see disagreements between models in parts of these parameter space where there are hatches, don't be alarmed. This could just mean that the models are making different priors, different model choices, and these can become important here. Okay, then let's look at the primary mass distribution, which is on the left. We see features like a global peak at 10 solar masses and also a feature at around 35 solar masses or so. The global peak is very robustly recovered, and this has been a feature in our data sets for a while now. And the understanding the origins of this global peak is very interesting. Understanding why we have so many black holes at 10 solar masses can be quite interesting, and we'll get deeper into this as the talk goes on, in later parts of the talk, I mean. The other feature is this 35 solar mass feature, which in previous data sets, we recovered it more. With previous data sets, we recovered it more as a peak at 35. But with GWTC 5, it is looking more like it could be a change in slope rather than a peak. The mass ratio distribution is on the right. This peaks at Q equals 1. So in other words, black holes like to pair with other black holes which have similar masses as them on the whole. But the distribution is fairly broad, and we do have support at lower Qs as well, indicating some support for asymmetric binaries as well. Next, let's look at spins. We'll start by looking at component spins. So the plot on the left shows the magnitude of the component dimensionless spins, and the plot on the right shows the distribution of the spin tilts with respect to the orbital angular momentum. So this is the spin tilt with respect to the plane of the binary, in other words. What we find is that black holes generally have smaller spins on the whole, most black holes. So 69 to 84% of black holes have spin magnitudes, dimensionless spin magnitudes less than 0.5. But this does have a long tail that goes all the way up to chi of 0.8 or 0.7. And indeed, when component spins are modeled uh, jointly, we find that about 9 to 24% of black holes host at least 9 to 24% of binary black holes host at least one rapidly spinning black hole with chi of 0.7. The spindle distribution is shown on the right, and we find that this distribution is fairly broad. And maybe there are indications that there might be a peak around cos theta of somewhere between 0 to 0.25. Another way to look at spins is to look at effective spins. Effective and there are two effective degrees of spin. There is the effective in-spiral spin, that's chi effective, and this captures the degree of spinniness that is perpendicular to the plane of the binary. So along the along the direction of the orbital angular momentum. The other spin parameter is the effective precessing spin, which captures the degree of spin in the plane of the binary. And these are spin parameters that we tend to measure better than component spins in general. And effective in-spiral spin in particular is probably the best measured spin parameter that we have, and it measures the degree of spinniness perpendicular to the plane of the binary. So let's look at this effective spin distribution that we recover. The plot on the left shows the effective in-spiral spin distribution. And I should say, by the way, sorry, that in each of these plots, each of these colored figures represent two different models. The salmon color generally represents the strongly parameterized model, and the blue is pixel pop, which represents the weakly parameterized model. And our contours give you 90% credible interval. So in other words, the solid line is the median, and the colored bars represent 90% credible levels. Okay, sorry about that. I should have mentioned this at the beginning. Okay, so let's look at effective spins. The plot on the left shows the effective in-spiral spin. And what we find is that this spin distribution, as recovered by both pixel pop, which is a weakly parameterized model, and the bivariate skew normal, which is our strong model, both of these indicates that the effective in-spiral spin peaks close to zero. But it has support both at negative values. So in other words, it has support that at least some fraction of binaries are anti-aligned with respect to the orbital and with respect to the orbital angular momentum. But it is also asymmetric. That is, it indicates that there are more binaries which are positively aligned with respect to the orbital angular momentum corresponding compared to binaries which are anti-aligned. And this asymmetry can tell us how many mergers are coming from formation scenarios which have preferentially aligned degrees of freedom, which are preferentially aligned. And what we find is that at least 9% of binaries, based on this asymmetry, we find that at least 9% of binaries originate from formation channels which have some degree of preferential alignment of the binary spin with of the black hole spin with the orbital angular momentum. The plot on the right shows the effective precessing spin distribution. We find that this distribution peaks away from zero, indicating some degree of precision in the populations. So there is support that at least some fraction of binaries have in-plane spin. And this is consistent with the fact that for the effective in-spiral spin, we recovered binaries having anti-aligned spins. Okay, so that's for the spins. Let's look at redshifts. We find that the plot here below shows the redshift distribution on the left, and we find that the redshift distribution is broadly consistent with star formation rate with a Maddow-Dickinson-like evolution with Z, which is shown using these dashed blue lines here. We do not recover any evidence for a peak yet, which is interesting but not perhaps surprising given that models suggest that peaks should happen at higher redshift than we are sensitive to currently. At low redshifts, the redshift distribution can be fit quite well using a power law. And we find that the power law index is about 2.5 plus or minus 0.7. So that's the salmon histogram here, and the corresponding GWTC4 value is shown in black. Okay, then we'll talk about correlations and stuff, and other things in the population, and I'll hand over to Max IC to talk about the next couple of sections of the paper.
Thanks, Sharan. So Sharan just introduced redshift into the picture, and we see that the rate of binary mergers increases with redshift. However, we have no indication that the shape of the mass distribution changes with redshift. On the other hand, we have known for some time that the chi-effective distribution, so Sharan, if we can go to the previous slide, chi-effective versus redshift. There we go. The chi-effective distribution has been known to show signs of broadening with redshift for some time, and we confirmed this with this latest GWTC5 catalog. We get at this result, as usual, with two flavors of models that you see represented here on the left: a more restrictive, strongly modeled linear model for these correlations, where a linear relationship is imposed between the mean and the width of the chi-effective distribution as a function of redshift. And on the other hand, a more flexible spline model that does not assume that this trend is necessarily linear, but can assume other shapes. And whether you use a linear model or a spline model, it appears that we have evidence for a broadening of the chi-effective distribution as you go further out in redshift. There is a degree of model dependence to this result, in particular if you're looking at the details of this broadening. Is it exactly linear, or are there features as a function of redshift? You can see on the left-hand side the top panel, which shows our estimation of the width of the chi-effective distribution as a function of redshift. In the spline model, there are more features that are allowed, but it's not clear at this level of credibility, given the data that we have, that this is significantly distinct from a linear trend. So for its part, the linear correlation model finds a preference for broadening at 93% credibility, which is quite significant. And you can see that represented as well in the population, in posterior predictive distribution on the bottom of this plot, where we reconstruct the implied distribution of chi-effective as a function of redshift. You see this red distribution broadening as you move from left to right. The spline model that's more flexible doesn't show such a marked trend. So within the regime of lower redshifts that we can constrain best with our data, it could accommodate no evolution. So there is some degree of model dependence to this result, but so we'll have to get more data to ascertain this, but it is consistent with some broadening in this distribution. Now, in terms of explaining this, of course, there's always a possibility that this correlation with redshift is entering through different parameters. So if chi-effective is correlated with the mass, for example, as will be mentioned later, or if it's correlated with mass ratio and that property itself evolves with redshift, then you may expect to see this evolution with redshift. So we explicitly look for correlations between chi-effective and mass ratio, for example, which is the next slide. And it has been pointed out for some time that there is some interdependence between chi-effective and mass ratio. And as of the previous gravitational wave catalog, it became clear that this dependence could be attributed either to the mean, so the location of the mode of the chi-effective distribution, or its width. And now with GWTC5, it has become clearer that the trend is stronger in the width. So if we ask, how does the chi-effective distribution evolve with mass ratio, we find that the mean of the chi-effective distribution does not seem to evolve very strongly with Q, but however, we do see a broadening, so that the more for lower values of Q, so more uneven asymmetric binaries, we tend to have a broader distribution of chi-effective. And so again, you see this on the left with both the more restrictive linear and more flexible spline models. And the top panel shows our estimate of the width of this distribution as on the y-axis as a function of mass ratio on the x-axis, and the corresponding chi-effective distribution is represented in the bottom panel. So again, to summarize, we see dependence of the width of the chi-effective distribution as a function of mass ratio, but not the mean. Okay, so far we have been talking about the whole population as a whole. For the rest of this presentation, we will start focusing on subsections of the mass spectrum, beginning on the next slide with the dominant feature, which is the peak that appears very prominently at around 10 solar masses. This peak, as Sharan mentioned, dominates the distribution. It contains between 60 and 80% of all the systems, as we inferred from the data. And of course, there is a lot of interest in trying to understand if these binaries in this region of primary mass, around 10 solar masses, also have other distinctive properties. In the past, there have been hints that the mass ratio distribution of these binaries could be distinctive from the rest, and in particular that they may favor a mass ratio of around 0.7 away or significantly away from unity. So that would mean that systems in this peak with primary mass of around 10 would preferentially merge with slightly lighter systems, so that the ratio would be 0.7 rather than 1. In GWTC5, with this latest data and our updated models, this preference, while still it can still be allowed, we have less assertive evidence in favor of it. So the GWTC5 data, while it can accommodate such a preference for Q equals 0.7 in this peak, does not require it. And so we see this result through a variety of models, and primarily on the left-hand side, we have a dedicated model that was constructed to study this peak in isolation from the rest of the population of binaries. And so this isolated peak model on the left side, the leftmost panel of this plot, models the mass distribution as a continuum that is supposed to capture everything except for the systems that are in a Gaussian peak around the 10 solar masses range. And each of these components, the continuum and the peak, can have its own independent spin and mass ratio properties. And so this allows us to directly ask the question, do these 10 solar mass binaries have any set of distinctive characteristics? So when it comes to mass ratio, we see that the mass ratio distribution is favoring systems that it is more likely closer to 1. So with overwhelming preference, these systems have mass ratio greater than 0.5. Whereas for the continuum, there's a broader distribution of mass ratios, which you see in blue. So the peak would be red, the continuum is blue. However, while there is a peak in this distribution that you see around 0.8 or so in the red curve on the left-hand side, it is not, these curves within uncertainty do not rule out that the rate at 0.8 is the same or less than the rate at q equals 1. So the rates at q equals 0.8 versus q equals 1 could be anywhere between 8 to 1 to 1 to 2. So within the uncertainties that we have, even though there is a slight preference for these uneven masses, we cannot rule out that it's actually equal masses are also equally favored. So this is this isolated peak model that is tailored for these sort of questions. We see something similar with more generic weakly modeled approaches like pixel pop that you see in the center and the bin Gaussian process that you see on the right most panel. Both of these approaches take a very flexible approach to this and use Gaussian processes of some kind to model the space of primary mass and mass ratio for pixel pop, and then primary mass ratio and chi-effective for the bin Gaussian process. And then we can subsegment the population in terms of primary mass and try to identify systems that are roughly in the 10 solar mass peak, so which in this case we define as systems within the range of 8 to 15 solar masses. And then we can ask similar questions again: do these systems have different mass ratio properties than the rest? And so you see that the bin Gaussian process result on the right-hand side is highly consistent visually with the isolated peak distributions that I discussed first, and similar conclusions apply. There could be some preference for mass ratio 0.7, 0.8, but it's not required. And that's definitely true also for pixel pop, where if you look at the red curve in the center, there could be a preference for uneven mass ratios, but it's definitely not strictly required. And so the bottom line again is that the evidence that this peak favors or requires a mass ratio that is definitively away from 1, it has diminished now with GWTC4. So this could still be the case, but we do not require it. In terms of other properties, in the next slide, we can also look at the spin distributions of binaries in this peak. And we find that the spin magnitudes of this of the systems in this peak can't have a broad distribution. So you can see this on the left-hand side from the isolated peak, which models explicitly the spin magnitudes individually of each component. The red curve is quite broad. It extends from 0 to 1. It is more peaked towards lower values than the continuum. So there is a preference for smaller values, just as we saw with the whole population, as Sharan mentioned earlier. In the case of the more flexible models, pixel pop and bin Gaussian process, the other two plots here, we model the effective spin rather than the individual spin magnitudes, but the story is the same. So in this case, we see that the red curves, which represent systems in the peak, are slightly more constrained than the blue curves, which represent the continuum, to have smaller chi-effective values, potentially with a slight preference towards positive chi-effective. You can see that these red curves peak slightly away from 0, and they are more tightly constrained than the blue ones. So nothing super different from the broad population, except since these systems are more abundant, we can constrain these spins quite well. Okay, we can move on to the next slide, which also moves us up in the mass spectrum. So far I have been talking about the feature around 10 solar masses, but the next feature is here, moving left to right on the mass spectrum, that is of interest occurs at around 35 solar masses. And for some time, it's been known that there's a feature here, whether it's a peak or a break, a change in the slope of the distribution was not always clear. With this GWTC5 data set, we appear to be able to determine more clearly that there's a preference for a break rather than a peak, in the sense that we can evaluate the rate before to the left of 30 solar masses, to the left of this feature, and it's consistent with being the same, whereas to the right, there must be a drop. So this, rather than this being a bump, this is really more consistent with a knee or a turnover in the mass distribution, whether you're looking at the primary M1 or the secondary M2. And I should say that this plot again comes from Pixel Pop. And now blue is the primary, red is the secondary. And what I just said in words, you can see in the plots, because you can draw a straight line from the left that then slopes downward, and rather than necessarily having to go up and then down. Another feature that you can see from this plot is that the turnover is more drastic for M2 than for M1. And so we will be calling this the 35 solar mass feature rather than the 35 solar mass peak, because that's what it appears to be, a turnover. We can also ask whether systems in this range have any other characteristic properties. So in the next slide, we go through a similar exercise as I've walked you through for the 10 solar mass peak. We can ask, do these binaries in the 35 solar mass range have any specific mass ratio, redshift, or chi-effective evolution? And so to begin with, on the upper left corner of this plot, if we look at binaries in the range of 25 to 40 solar masses for the primary mass, and we ask what are the mass ratios, we find a preference for equal masses, but this is, and this comes from the fact that these curves, both from Pixel Pop in blue and the Bin-Gaussian process in red, are peaking at 1, so Q equals 1, which means equal mass pairings. However, it's a slight preference statistically, just for the same reason as I discussed for the 10 solar mass case. So, there's a range. We could still allow for some gradient here, but we cannot. This is totally consistent with these distributions just peaking at 1. Okay, so the mass ratio you see on the upper left. Then on the upper right, you see a reconstruction of the redshift evolution of the rate for systems within this peak. This is not significantly different than the overall population. It's again consistent with the star formation rate, so not super distinctive here either. Now for the spins on the lower left panel, you see now reconstructions of the chi-effective distributions, again with Pixel Pop and Bin-Gaussian process, 2 weakly modeled approaches, which both agree that the distribution of chi-effective for systems in the 25 to 40 solar mass range is quite broad, again favoring low values. A difference here with the 10 solar mass peak is that there isn't necessarily a clear preference for a shift towards towards positive chi-effectives. So these curves are consistent with being centered at around 0 and having equal numbers of systems with negative as positive chi-effective. And you see that summarized on the bottom right panel, which looks at what is the fraction of systems that have chi-effective being negative. And in the case of Pixel Pop, that's totally consistent, and it peaks at 0.5. And the Bin-Gaussian process may have a slight preference for more positive chi-effective systems, but it's again within the uncertainties totally consistent with a 50-50 split. So this is slightly different if you're looking at the 10 solar mass peak, where there was more of a marked preference for positive chi-effective. Okay, I think this brings us to the end of the 35 solar mass feature. And so I'm happy to hand it off to Hui to move up in the mass spectrum.
Thanks, Max. So Max just introduced the black hole features around 10 solar mass and 35 solar mass, but we do observe more massive binary black hole systems than that, like GW 1905-21 and GW 2311-23. So the mass scales of these very massive events locating a mass range that's much higher than the 35 solar mass peak. So this high mass region could be fascinating as well due to the theories like period stability supernova. So stellar theory predicts one type of supernova from massive stars at certain mass range whose explosion is strong enough and no remnant will be left behind. So the absence or presence of the feature like upper mass gap in the black hole mass spectrum as predicted by period-stability supernova could be interesting for astrophysics, including stellar evolution, period-stability mechanism, and black hole formation environments. So in these slides, we're getting back to the figure that's showing the black hole mass spectrum, but let's focus on the high mass parts at this time. So Sharan and Max mentioned there could be a break around 35 solar mass, which appear both in the M1 and M2 distribution. This results in a sharper decline for the mass distribution for both components compared with their lower mass region. But if we just focus on this high mass range, when comparing the distribution of M1 and M2, both at the high mass region, the M2 distribution declines more rapidly than M1 at over 40 solar mass. So if we could go to the next slides, the difference of the slope of this high mass spectrum between M1 and M2 is physically consistent with a flatter mass distribution for those high mass systems. Here we present the mass ratio distribution for high mass systems using both a strongly parameterized model, which models the high mass subpopulation separately, and again, the weakly parameterized model in blue, the pixel pop, but here we truncate it above 45 solar mass to focus on the high mass region. So the results from different approaches are quite consistent with each other, and as I mentioned, they both showing a relatively flat mass ratio distribution with a peak around 0.5. And moreover, the strongly parameterized model actually allows the onset of this high mass subpopulation as a free parameter. So we infer the starting point of this high mass subpopulation, which presents distinct properties at exactly around 45 solar mass. That's why we chose this 47 solar mass. That's why we chose this 47 solar mass for our weekly model to show the mass ratio distribution accordingly. So interpreted such transitioning of binary black hole mass spectrum at high mass as evidence for contamination from alternative formation channels, and potentially this could be the impact from period stability supernova physics. So next slides. One common contamination channel for those high mass systems that people widely consider is hierarchical mergers. So some fraction of the remnant of previous binary black hole mergers in dense stellar environments can be retained and merged with another black hole again. We call such repeated mergers as hierarchical mergers. So the remnants, which we named as the second or even higher generation black holes as a product of previous mergers, do not, but not formed directly from stellar collapse, could be a natural explanation of black holes that populate the period stability gap. So the hierarchical mergers are predicted to have distinct features. As an example, on the right-hand side, we show the masses and spins of two most promising hierarchical merger candidates in our catalog to date, GW241011 and GW241110. So both systems show strong spins of their primary components. The heavier one, as shown here at Chi1 for these two events, and they appeared with a possibly first generation black hole to merge, which also results in very unequal mass ratio here. So those kind of 1G, 2G mergers in dense stellar clusters could have very specific falsifiable spin signatures. The primary component as the second generation black hole should have spin magnitude around 0.7, and assuming an isotropic spin orientation and a typical 2G plus merger mass ratio around 0.5, this will lead to an uniform chi-effective distribution centered around 0 and with a half width as 0.47. So in this paper, we look into the hierarchical mergers as a population level, but not only focusing on the exceptional events. We try to search for the fraction of binaries as a function of primary mass that are consistent with hierarchical signature. So if we can go to next slide, that's the result. Zeta 1 here is the fraction of the black holes consistent with a chi-effective distribution as a very broad uniform distribution predicted by 2G plus 1G mergers. So the figure displays a non-trivial peak of this fraction. So there's a pronounced low mass peak around between 10 to 20 solar mass, where the two exceptional events just locate. And the median of zeta 1 around this region could rise up to 70%, and followed by a dip after 20 solar mass, and a second increase above around 40 or 45 solar mass. So data therefore supports the presence of multiple mass scales at which a broader, approximately uniform chi-effective component becomes relevant. So this trend is also supported by the results from a separate model, which we explicitly parameterize the discrete mass scales according to the transition of spin properties. So here we show the results, amplitude low, amplitude mid, amplitude high. The location of these parameters qualitatively consistent with the fraction change. So which made us confident that those kind of transitioning in the spin properties are true. And yeah, just to close up, the full GWTC 5 catalog contains 267 binaries and presents our deepest analysis into the population of merging binaries yet. And we see distinct evidence of black holes with rapid spins, and also growing evidence of multiple subpopulation of binaries. And GWTC 6 will build upon these results further, so stay tuned for our next data release. And I'll end here and happy to take any questions.
Thank you, Max and Wei. So yeah, at this point, I think we'll open the floor for questions. Casey, I can't see the. Oh no, there we go. Yeah, sorry, Casey. I think I can't see the question ticker. So if you are able to see that, would you be able to ask questions, please?
Yes. So we did have one question in the Q&A that has been answered, but for the sake of the recording, I'm happy to answer. The question was, can I ask why these rates, like for the mass distribution, are often shown at z equals 0.2? Is that the best measured one?
Yeah, I think especially for binary black hole mergers, z equals 0.2 represents close to the redshift where we measure the merger rate the best, and that motivates using a z equals 0.2 for BBH mergers. You will notice, I can actually go back, you'll notice that for binary neutron star and neutron star black hole mergers, we are still reporting the rates at z equals 0. So these are local rates because we don't usually have good measurements of VNS and NSBH mergers up until z equals 0.2.
Okay, and then there looks like a follow-up question. So 35 solar mass peak is not astrophysical, since you mentioned it is not peak anymore with GWTC 5 analysis.
maybe Soumendra, who's on the panel, can take that.
Yeah, not necessarily. So at 35 or near 35, between 30 to 35, we actually see a break. So that needs to have some astrophysical explanation. So there is no reason that it will continue like the same distribution. So it's not a peak, definitely. Like we don't see that in GWTC 5, but that break needs to have some astrophysical explanation. Understand?
And there are currently no other questions in the Q&A.
Okay. Maybe if there are no other questions, then we will close out the webinar at this point. So thank you everyone again for joining the webinar, and thank you for all of the panelists. And we will have another webinar in 2 hours on open data and TGR. But otherwise, have a good rest of your day. Thanks everyone. Bye.